Every time you use Google Maps or connect your phone to GPS, you rely on the physics of time moving differently at high speeds and higher altitudes. Those engineering corrections show how relativity affects our daily lives, but Einstein's equations go even further, predicting that along the path of light itself, the passage of time becomes zero. That raises a profound question. Could time truly vanish at the speed of light? In 2025, new research is sharpening this mystery. JILA physicists measured time dilation across a single millimeter with cutting-edge atomic clocks, while particle collisions at CERN revealed updated entanglement effects near light speed. These advances push Einstein's puzzle to the smallest and fastest scales we can observe. So why does something as ordinary as time begin to behave so strangely when speed increases? The strange relationship between time and light. At the center of this discussion lies the strange connection between light, motion, and time itself. Ordinary experience anchors us to the idea of time moving steadily forward, yet the rules of physics show something very different once light enters the picture. At speeds approaching light, seconds no longer align, and clocks disagree on how much time has passed. For light itself, the one thing in the universe that always moves at this maximum speed, the mathematics of relativity indicates that time, as normally defined, has no role at all. This insight arose in 1905, when Albert Einstein's theory of special relativity overturned the assumption that space and time exist as separate, universal backgrounds. Instead, they form a single geometric fabric known as spacetime, where an object's path through space must always balance with its passage through time. Moving faster through space reduces movement through time, meaning that one cannot accelerate without consequence. At low speeds, this imbalance is undetectable, but as speeds climb toward light itself, the changes become too large to ignore. One simple way to picture the effect is with two identical clocks. Leave one on a desk at home, while the other joins a spacecraft accelerating close to light speed. When both are later compared, the traveling clock will mark fewer ticks. This thought experiment has real-world confirmation. In the 1970s, aircraft carrying atomic clocks returned measurably out of sync with those that stayed grounded. Modern experiments have sharpened these results far beyond aviation. In 2014, particle accelerators timed lithium ions moving at tens of thousands of kilometers per second, confirming that their internal clocks slowed exactly as relativity predicted. In 2022, JILA researchers showed measurable time dilation across just 1 millimeter, using optical lattice clocks sensitive enough to detect gravity's pull at that scale. Together, these experiments anchor relativity as a tested and practical description of how time shifts under both speed and gravity. Imagine now what happens as motion approaches the cosmic speed limit. For people in a near-light-speed ship, biological rhythms, heartbeat, breathing, and even cellular activity would all slow relative to those left behind. The passengers would feel unchanged, but once reunited with others, they would discover that far more time had elapsed in the outside world. That is time dilation made real, a consequence of being massive objects moving close to light speed. However, the laws of physics impose a hard boundary. As velocity climbs, the energy required for further acceleration grows without limit. For this reason alone, massive things, humans, spacecraft, or even single atoms, cannot ever reach the exact speed of light. This brings us to photons, the carriers of light. Unlike anything with mass, these particles always move through the vacuum at precisely light speed, with no need for acceleration. Here, relativity gives a striking mathematical result. Along a photon's path, the quantity called proper time is zero. Put another way, special relativity does not allow a valid inertial rest frame for light itself. Physicists sometimes say that light experiences no time, but this is shorthand for the rigorous idea that a photon's world line stretches across space without any interval in its own proper time. To outside observers, A photon might travel for billions of years across the cosmos. Within the framework of relativity, however, no duration attaches to that journey. This distinction is important because it marks the edge of what the theory can describe. Humans can approach light speed in thought, but cannot attain it in practice. Spaceships and astronauts have rest mass, and so remain fully subject to time. The notion of time stopping at light speed is therefore only a mathematical expression, not a physical state available to us. When said carefully, it refers to the way special relativity compresses proper time to zero for any worldline at exactly light speed. Confusion arises when this phrasing is taken too literally. Still, the implications are profound. If light has no internal clock ticking from one end of its journey to the other, then time may not be a universal stage set on which events unfold. Instead, it is a relative measure that depends deeply on the properties of the traveler. Relativity already showed us that motion through space alters time's passage. Now photons highlight the extreme possibility, a condition in which the familiar rhythm of time does not appear at all. This contrast tells us something fundamental about the difference between things that possess mass and those that do not. None of this is speculative. Around us, technologies must constantly adapt to these relativistic rules. Satellites orbiting Earth require adjustments to keep their time systems aligned with ground clocks. Particle accelerators confirm relativistic effects every time high-speed ions decay more slowly than expected. Light from distant stars provides both a clock and a mystery, arriving billions of years after departure while still carrying no interval of proper time along the way. Everyday tools and cosmic signals alike are grounded in this strange relationship between light and time. For physicists, the lesson is clear. The closer something comes to light speed, the more severely its perspective on time diverges from that of slower observers. For light itself, the measure of time collapses into mathematics without human analogy. And for us, bound by mass and energy, the speed of light is a limit we cannot cross, but one that defines every constant of the physical world. The full significance of this becomes far more tangible when we look at technology that depends on these effects to work correctly. Only then do the abstract predictions of relativity reveal themselves in ways that touch everyday life, from navigation to global communication. When time runs differently, GPS is proof. Every time someone checks a phone for directions or watches a car's navigation system trace out a route, they are quietly relying on a reminder that time does not tick at the same pace everywhere. The global positioning system feels straightforward. Signals broadcast from orbiting satellites, receivers compare them, and a precise location appears. But what holds the system together is not just radio transmission. It is the alignment of clocks that mark time differently depending on whether they sit deep within Earth's gravity or speed overhead in space. Without those corrections, the GPS network would unravel in hours. The satellites orbit Earth at nearly 4 kilometers per second. That motion produces a special relativity effect, where moving clocks tick slower than stationary ones, reducing satellite time by about 7 microseconds for every day in orbit. But something else also acts, the gravitational effect described in general relativity. Higher above Earth's surface, gravity's pull is weaker, and in this environment clocks run faster, adding about 45 microseconds per day. The two influences pull in opposite directions, and when combined, they do not cancel. Together, they leave the satellite clocks running about 38 microseconds ahead of those on Earth's surface each day. 38 millionths of a second may sound negligible, but GPS must achieve accuracy within a few nanoseconds. A mismatch that large would shift measured positions by kilometers daily. Within a week, the errors would grow into tens of kilometers, turning every phone and aircraft display into a misleading guide. Navigation systems, shipping routes, and air traffic would all be degraded. In that sense, relativity is not a side detail, it is a requirement. The time corrections needed to counter these relativistic effects are what keep our maps aligned with reality. Engineers solved this challenge with careful design. Before launch, each satellite's onboard atomic clock is tuned with a frequency offset so that once in orbit, ticking proceeds in harmony with identical standards on the ground. This factory offset corrects the net plus 38 microseconds per day discrepancy that relativity guarantees, but further complications remain. Orbits are not perfect circles, so speed and altitude vary slightly. As satellites pass through different parts of their orbits, their clocks drift by tens of nanoseconds. To prevent this fluctuation from accumulating into further distance errors, the network applies real-time corrections calculated on Earth and uploaded to the satellites. Through these adjustments, the constellation of more than 30 satellites stays synchronized, and receivers can exploit overlapping signals to calculate positions within a few meters. The reliance on this synchronization demonstrates how directly physics becomes part of engineering. Each positioning fix requires that signals traveling at the speed of light be timed against one another at the scale of billionths of a second. A single nanosecond error corresponds to a path difference of about 30 centimeters. By working at such precision, engineers cannot ignore effects that seem insignificant in most contexts. 7 microseconds lost from motion and 45 microseconds gained from weaker gravity add up to thousands of nanoseconds, and that in turn would cause vast displacements on Earth's surface. The technology works only because it constantly applies relativistic corrections. If those corrections were ignored, the consequences would appear quickly. Imagine disabling the relativity settings for a day. Clocks in orbit would accumulate tens of microseconds of offset. GPS receivers would interpret signals as arriving too early, and the mismatch would shift ground positions. At first, a person following turn-by-turn directions might notice instructions pointing slightly ahead of the car's true location. After hours, deviations would build into hundreds of meters. After a full day, navigational errors could measure 10 kilometers or more. For aircraft, this would mean straying off established airways. For ocean vessels, routes plotted from GPS alone would drift far from intended paths. Everyday transportation, finance networks depending on time stamps, agriculture, and surveying would fail to function with precision. The degree of urgency that relativity forces on GPS can be seen by comparing these numbers to the demands of accuracy. A 10 nanosecond time error is already enough to shift calculated positions by 3 meters. Engineers need atomic clocks versatile enough to maintain stability to within a few billionths of a second per day. Any greater drift would break the network's coherence. That is why GPS became one of the most prominent real-world systems to embody Einstein's predictions. No clock in orbit can be built without planning for how gravity and velocity stretch or compress the measurement of seconds. This feature of GPS also explains why the system works equally well across the globe. Engineers must compensate not only for orbital effects, but also for Earth's own shape and motion. At different locations on Earth's surface, gravitational potential and speed from rotation vary. Yet the combined effects conspire in such a way that time on the surface synchronizes uniformly, while in orbit the effects diverge and must be corrected. That design is what allows position fixes to appear stable whether in a city street, at sea, or on an aircraft crossing continents. The contrast is striking. In laboratories, physicists use atomic clocks to study relativistic time shifts across heights of a few centimeters. In orbit, satellites carry clocks that demonstrate those same principles on a global scale, every moment of every day. These orbiting instruments are not just transmitting coordinates. They are part of a continuous experiment verifying relativity's prediction that speed and gravity alter the pace of time. Every successful map pin and every accurate landing is evidence that Einstein's theory is part of the infrastructure of modern life. This integration has another effect. It changes how physics is perceived beyond laboratories. Relativity is not optional background knowledge for specialists. It is a silent requirement embedded into the electronics that billions of people use daily. Instead of serving only as an intellectual model of the universe, the theory directly stabilizes applications no society would choose to risk losing. That necessity underlines the point. Relativity is woven into devices we take for granted, and our trust in global positioning remains possible only because engineers treat its predictions as mandatory. Each corrected signal from a GPS satellite thus confirms something extraordinary. Time does not advance uniformly, and technological achievements depend on acknowledging that. Every flight guided, shipment tracked, or phone query answered owes its reliability to the fact that clocks diverge in orbit from clocks on Earth, and that divergence is reconciled by relativity. And yet, correction of these orbital clocks is only one part of physics confronting the fact that time flows differently under different conditions. The same question arises in another direction. What happens when we try to accelerate matter itself to ever higher speeds, reaching closer and closer to the ultimate limit at which light travels, pushing matter toward light speed? Our closest window into what happens as matter nears the ultimate speed limit comes from machines built to push particles with almost unimaginable force. These are particle accelerators, vast structures that use magnetic fields and electric gradients to guide charged fragments of matter until their motion nearly matches that of light itself. Instead of trying to hurl entire vehicles or people, researchers focus on the smallest building blocks, protons, electrons, and heavier nuclei, because they can be driven to extraordinary velocities under controlled conditions. Watching how these particles behave reveals the practical limits of relativity in action. The most powerful of these instruments is the Large Hadron Collider beneath the border of France and Switzerland. Stretching over a 27-kilometer underground loop, it was engineered to sustain beams of protons at energies so high that everyday intuition ceases to be a useful guide. By the time protons are circulating in its magnetic field system, they race at about 0.9999999 times the speed of light. At such speeds, their Lorentz factor, a measure of how relativistic effects grow, soars into the thousands. This makes the LHC the closest laboratory analog we have to an environment where matter brushes against light's ultimate pace, and why its experiments provide the clearest demonstrations of relativity under stress. What sets these conditions apart is not that the particles keep gaining velocity in the usual sense, but that most of the added energy is diverted elsewhere. Special relativity dictates that, as the velocity of a massive particle inches toward light speed, the required energy to continue accelerating it rises out of proportion. This additional energy does not make the protons move noticeably faster, since their speed is already within a whisper of the limit. Instead, the energy swells the particle's relativistic mass and dramatically alters the way time flows when viewed from an outside reference frame. If a proton could carry a clock, that clock would appear to outsiders as ticking more slowly with each incremental rise in energy. This reality is made visible with particles whose natural lives are fleeting. Muons, heavy cousins of the electron, normally decay in only about 2/millionths of a second when left at rest. Yet when these muons are produced inside accelerators at nearly light speed, laboratory detectors record them surviving for thousands of times longer than their stationary lifetime. The effect is not that the particle becomes more stable, but that time itself is stretched relative to our perspective. The muon still experiences its same proper 2 microseconds, but because of time dilation in the laboratory frame, it travels much farther before disappearing. The fact that detectors can measure this extension with precision makes muons a direct and highly persuasive confirmation of Einstein's predictions. Similar demonstrations appear naturally in the atmosphere. High-energy cosmic rays colliding with molecules overhead generate showers of muons that rain downward. By all calculations, their normal 2 microsecond lifetime should allow them to travel only a few hundred meters before decaying. Yet countless muons are measured at the Earth's surface, having survived journeys of tens of kilometers through the air. Their improbable arrival makes sense only if time dilation has extended their observed lifetimes, a phenomenon independently verified under controlled conditions inside accelerators worldwide. These parallel cases, one in laboratory rings and the other high in the atmosphere, reinforce each other. Relativity predicts the dilation, and nature confirms it. The reach of accelerators extends far beyond verifying lifetime extensions. Their collisions break apart protons into showers of more elementary particles, producing conditions that last existed only fractions of a second after the Big Bang. The discovery of the Higgs boson in 2012 was one of the defining achievements of the LHC, but ongoing runs continue to uncover subtleties in particle interactions. In 2024, the ATLAS experiment recorded evidence of quantum entanglement between quarks at unprecedented energy, underscoring how strange and interconnected the quantum world becomes at relativistic extremes. Yet behind these landmark announcements lies the same foundation. All of it is possible only because accelerators reliably push matter into the near-light speed regime, where relativity dictates the rules. It is important to note that none of this implies we can directly scale these results up to the everyday scale of ships or humans. Accelerators succeed because they manipulate subatomic particles with vanishingly small mass, using field gradients and superconducting magnets capable of forcing them onto near-light trajectories. The method works because the particles themselves are tiny and carry charge, making them responsive to electromagnetic control. No known engineering approach could replicate this on macroscopic objects like spacecraft, which involve incomparably greater rest mass and different physical constraints. The experiments teach us what happens to matter under those conditions, but they do not offer a blueprint for human travel at such speeds. The inescapable obstacle remains the structure of relativity itself. Each increment toward light speed requires more and more energy, with the demand climbing so steeply that it approaches infinity before the limit is ever reached. The LHC's colossal energy input and the billions of dollars invested in its infrastructure are required just to elevate tiny groups of protons to conditions that remain infinitesimally short of light speed. This escalating cost signals why nothing bulkier can ever achieve the same threshold. Calling it a barrier is not a figure of speech. It reflects a mathematical limit built into the geometry of spacetime. Over the past 2 decades, advances in accelerator design have pushed data quality to the level where relativistic predictions are confirmed to astonishing precision. Each measurement of lifetime extension, each observation of decay signatures shifted far from their rest frame expectations, strengthens the conclusion that the laws Einstein laid down survive under the harshest conceivable tests. Sophisticated detectors record billions of collisions, while teams refine equations to within microfractions of a percent. Far from remaining abstract 20th century ideas, relativity's principles are demonstrated daily in sprawling facilities that bring them to life through beams of particles moving at 99.999999% of light speed. Even so, what strikes researchers most is how sharply the curve bends as particles press ever closer to the limit. At modest fractions of light speed, the dilation of time is slight, hardly noticeable. But push into the realm of 0.999999999 C, and the effect grows monumental, inflating particle lifetimes and stretching intervals beyond everyday comprehension. This runaway escalation shows why attempts to imagine continuing the process to full light speed are not merely impractical, but ruled out by the theory itself. Our instruments therefore give us both a tool for discovery and a warning written into physics. Accelerators demonstrate vividly that relativity is real, measurable, and unavoidable. But they also emphasize that the same rules preventing infinite acceleration in a laboratory apply universally. Particles supply their own answer about the unattainability of light speed by showing us what happens as you try. Greater energy yields more dilation and more resistance, yet never the final goal. These lessons drawn from tiny particles prepare the ground for the question that naturally follows. If even the most elaborate machines on Earth fail to carry matter across that final threshold, what hope would there be for something larger? The impossible barrier of light speed. The barrier that defines the edge of possibility is the light speed limit itself. Special relativity makes clear that no object carrying mass can ever be accelerated fully to that velocity. The equations describe why. As velocity gets closer to the speed of light, the Lorentz factor, represented by the symbol gamma, climbs sharply. Because kinetic energy grows proportionally to gamma, each small increase in speed demands more energy than the one before. Near the limit, gamma trends toward infinity, which means the energy required also trends toward infinity. This mathematical rise is not just steep, it is unbounded, and that is why relativity describes light speed as an uncrossable threshold. The distinction between matter and light is central to understanding this boundary. Photons do not have rest mass, so they are not subject to the same acceleration rules. They simply exist in motion, always traveling at c, the constant speed of light in a vacuum. Matter, however, carries rest mass. Moving it faster requires supplying energy, and as velocity approaches c, that task becomes overwhelmingly difficult. At walking or even rocket speeds, burning chemical fuel is sufficient to overcome inertia. At fractions of c large enough to alter time perception, fuel demands no longer match what any propulsion method could produce. The conclusion from relativity is that no resource or engine can overcome this wall, because infinite energy does not exist in nature. A useful analogy is the act of sliding a heavy block. Once moving, it can be pushed along with manageable force. Imagine, though, that with every meter you shove it grows heavier. Eventually, the required force would surpass your strength entirely. That is how the resistance builds for any particle with mass. The mathematics says the increase never stops until the barrier is reached, yet that frontier can never be touched because the needed energy supply escapes all possible limits. Accelerator data confirm this relentlessly. The faster particles are driven, the more energy goes into sustaining barely perceptible gains in additional speed. It is the laboratory mirror of the same divergent curve that no technology can overcome. This barrier means matter and light occupy permanently distinct categories. Photons glide along at c, while everything with rest mass sits below. Any attempt to design spacecraft capable of equal speed collides with that fact. Every kilogram on board, whether hull, fuel, or cargo, would demand an unbounded energy supply to cross the final gap. Even the output of stellar furnaces scattered across galaxies could not add up to what is required. This is not a technological blockade, but a structural one, tied to the nature of spacetime itself. Time dilation, another prediction of relativity, reinforces the limit from a different angle. As speed increases, an onboard clock runs slower than the clocks left behind. Extend this to extreme speeds, and the difference grows to staggering levels. For an outside observer, the traveler seems frozen almost in time. But relativity makes clear the clock never reaches full stop. There is always a tiny fraction of ticking left. This outcome parallels the infinite energy requirement. Both features describe the same constraint with different language. The flow of proper time for a massive traveler never halts completely, and the energy demand to reach c never converges on a finite value. It is tempting to imagine pressing forward regardless, but practical barriers appear well before infinite energy enters the picture. At extremely high fractions of light speed, both material stresses and radiation hazards escalate. Interactions with stray particles become progressively more dangerous, and mounting energy levels translate into heightened challenges for any physical structure. Even without detailed calculations, it is clear that survival conditions worsen rapidly once speeds approach relativistic extremes. These issues stand alongside the theoretical energy wall, reinforcing why matter cannot survive transit close to light speed. What matters most is that this conclusion has remained stable across every domain tested so far. Satellites orbiting Earth, aircraft carrying clocks, laboratory particles accelerated to nearly c, all align with the same mathematics. Nothing has hinted at an exception, and nothing suggests that matter can blur the line separating it from photons. The laws do not bend according to circumstance. Spacetime retains this distinction under every set of observations. That constancy explains not just why spacecraft cannot reach light speed, but why our universe retains its consistent structure. If matter could exceed this ceiling, cause and effect themselves would fail. Faster-than-light signals could arrive before they were sent, and different observers could disagree on whether one event caused another. The barrier preserves order. Photons race at the cosmic limit, but everything with rest mass remains slower, and by staying slower, the sequence of events remains predictable. The speed of light is not simply the fastest speed known. It is the foundation that locks in time, order, and causality. Yet even as the barrier proves absolute, its very presence continues to drive speculation. Scientists and engineers have long wondered whether there could be loopholes not in mass, but in spacetime itself. If the problem lies in trying to accelerate matter through ordinary space, perhaps the pathway forward would have to involve space being reshaped or shortened. Exotic models such as wormholes or spacetime distortions emerge from this impulse to imagine alternatives. But while ideas like these persist, they remain speculative, without empirical support to suggest practical use. Current physics has shown, consistently, that the wall at light speed is not a gap waiting to be closed, but a limit supported at every level we can probe. Accelerators confirm time dilation and energy divergence. Satellites validate relativistic corrections to nanosecond scales. Cosmic particles display lifetimes extended far beyond expectations at rest. Each observation builds the same picture piece by piece. Mass cannot arrive at c. The consistency of these results over more than a century indicates that relativity does not hide exceptions within the ranges we can examine. So when the question arises of why no light-speed craft has appeared, the answer is not lack of vision but the mathematics written into nature. Infinite energy is needed to reach the barrier, yet the universe presents no inventory large enough to meet that demand. Mass, inertia, and spacetime together hold objects below light speed, and photons remain the only carriers permitted to cross that ultimate threshold. That is why scientists describe the barrier not as something awaiting clever engineering, but as a fundamental property of the universe. It holds the distinction between matter and energy steady, secures causality, and has been confirmed repeatedly from the smallest scales to astronomical distances. For now, it stands as physics' most reliable boundary. But limits often inspire new kinds of questions. If mass cannot cross the line by force, could spacetime offer a way around it? Faster-than-light ideas, science fact or science fiction. The idea of going faster than light has long fascinated both science and fiction. The most prominent theoretical tool for imagining it is what physicists call a warp drive, and the most widely known version is the Alcubierre model. Proposed in 1994 by Miguel Alcubierre, this model does not try to accelerate a spacecraft beyond light speed directly. Instead, it imagines creating a bubble of warped spacetime, contracting the space ahead of a vessel and expanding the space behind it. To outside observers, the ship would appear to move across enormous distances faster than light could travel. Yet inside its bubble, the craft would remain at rest relative to local spacetime, never breaking relativity's rules or subjecting passengers to extreme accelerations. On paper, it works as an elegant workaround, but the equations reveal obstacles that are far greater than engineering challenges. The first and most critical obstacle is energy. Alcubierre's metric requires spacetime to be curved with regions of negative energy density, something not available in usable form. This exotic matter has never been observed in bulk. The Casimir effect, measured between closely spaced conducting plates, does demonstrate negative energy at tiny scales, but only in minute fleeting amounts. These effects are many orders of magnitude too small to stretch or compress spacetime on the vast scale needed for a transport bubble. Early calculations showed that to form a bubble large enough to carry even a modest spacecraft, the negative energy required would exceed the total energy available in the observable universe. This severe mismatch makes clear that while the Alcubierre model is mathematically consistent, it is not physically realizable with anything close to existing or foreseeable technology. Even so, theoretical refinements since the 1990s have sought to reduce these overwhelming demands. The original design wrapped the vessel in a spherical shell of warped spacetime. Later analyses suggested that reshaping this shell could lower requirements. Configurations that use a toroidal or ring-like bubble geometry require far less negative energy than spherical versions. Though still unreachable, these adjustments bring the demand down by many orders of magnitude on paper. Physicists such as Chris van den Broek proposed nested or compressed bubbles that shrink the required exotic energy still further, narrowing the gap between mathematical theory and physical plausibility. Meanwhile, Harold White at NASA's EagleWorks laboratory examined variations in bubble geometry that might reduce requirements by additional factors. These refinements offer models with smaller footprints but remain speculative exercises, because even after reductions, the energy costs remain impossible by human standards. Beyond changing bubble shapes, other approaches explore whether exotic matter might not be needed at all. In 2020, physicist Eric Lentz proposed that a soliton-like configuration, stable, localized waveforms in spacetime, might create a propagating warp bubble supported by positive, rather than negative, energy densities. Like the Alcubierre drive, this solution remains purely theoretical, but it demonstrates that mathematical frameworks for superluminal travel are not strictly bound to exotic matter. Others have focused on subluminal warp models built from similar principles. These would not exceed light speed, but could still allow highly efficient motion at near-light velocities while reducing stresses on structures and passengers. Such theoretical variants broaden the landscape. Some aim for actual faster-than-light travel, while others look for practical designs that, even without breaking the light barrier, could revolutionize how propulsion works. Research has also branched into exploring whether metamaterials could assist in controlling fields. Gravitational metamaterials, for instance, are an idea proposed to manipulate spacetime in engineered ways, just as optical metamaterials bend light. If such materials could be manufactured, they might interact with gravity in helpful patterns, potentially reducing the burden of negative energy. Again, these ideas sit at the level of speculation. No such material exists, and the concept remains entirely untested. But the mere fact that researchers are entertaining such models reflects a broader scientific willingness to explore whether spacetime can be manipulated in complex ways, rather than abandoned as impractical by definition. For all these variations, the same challenge persists. No laboratory has ever generated or stabilized anything recognizable as a warp bubble. The gap between a mathematical metric and a controllable structure in spacetime is enormous. Experimental work to date has focused on instruments designed to detect very slight distortions. Harold White's team, for example, developed the White-Jude interferometer to look for microscopic signals that could correspond to energy-induced warps. These efforts target the smallest possible scale, asking if space can be nudged locally before imagining any large-scale application. No convincing evidence has yet been observed. The effort reflects a research pattern seen across physics. Theoretical predictions often precede experiments by decades, and progress comes first from learning whether even tiny versions of an effect can appear. If warp travel were possible, its implications would reach beyond engineering. Faster-than-light movement would violate the normal ordering of events in relativity, where cause is always required to precede effect. Arriving sooner than light could mean arriving before signals announce departure, raising the possibility of paradoxes. Researchers such as Tim Dietrich note that causality underpins every known law of physics. To rupture it could destabilize the very logic of natural law. While science fiction portrays paradoxes as narrative devices, in physics they are potential proof that a proposal is not consistent with existing theories. Any serious consideration of superluminal travel must, after energy costs, confront how it might preserve a meaningful causal order in a universe built upon it. Speculation has even extended to how such drives would reveal themselves if ever built by other civilizations. Calculated models suggest that collapsing or unstable warp bubbles might emit bursts of gravitational waves outside the normal spectrum of astrophysical phenomena. Sensitive instruments like LIGO and Virgo could, in principle, detect strange ripples if they ever passed Earth. Light stretched and shifted ahead, and behind a warp bubble would also appear unusual. Objects ahead would shift toward the blue, while those behind would appear redder than expected. No such signals have been detected, but researchers note that looking for anomalies resembling these patterns could serve as a search strategy if warp technologies have been mastered elsewhere. These proposals remain hypothetical, but they draw interest because they offer concrete observational markers for otherwise invisible technologies. Refinements published through the 2020s keep fueling interest. Some papers describe multi-layer warp bubbles, stacking surfaces so that each layer carries a fraction of the total energy burden. Others explore tailored wall thicknesses or bubble geometries that distribute stresses more evenly. Energy tallies have shifted from entirely hopeless values, the energy of the visible universe itself, to figures that remain monstrous but reduced by dozens of orders of magnitude. Though such shifts do not open doors to construction, they encourage efforts to push the math further and see whether unknown physical effects might someday reduce figures to realistic levels. Computational resources, machine learning, and artificial intelligence are increasingly used to scan through the sprawling parameter space, surfacing configurations that optimize efficiency. Even if practical warp drives never emerge, this computational push deepens our understanding of spacetime solutions more broadly, contributing insights back to cosmology and field theory. Despite the persistence of new models, the real-world state of affairs is straightforward. Spacecraft in 2025 still rely on chemical rockets, ion drives, and developing nuclear propulsion technologies. The Alcubierre bubble remains a mathematical curiosity, not a prototype. Substantial breakthroughs will be needed in physics and engineering before such ideas can take root in laboratories, let alone be applied to vehicles. But the continuing examination of warp drives plays an important role in pushing researchers to confront physics at its extremes. By testing whether negative energy, solitons, or gravitational control can exist in useful forms, scientists probe the limits of current theory and sometimes discover insights far from the field's original intention. That is why faster-than-light concepts continue to sit uneasily between speculation and science. For now, they highlight how imagination and mathematics together stretch the boundaries of what we think possible. They also remind us that even when one boundary appears unshakable, creative work can expose new routes for questioning the structure of reality. It is in this sense that exploring FTL travel remains valuable, not for its engineering payoff today, but for the way it sharpens scientific inquiry. And from such inquiries, future physics may reveal other ways time and space behave that remain far outside our current intuition. These questions matter because they link directly to the other major puzzle in physics, the nature of time itself. While relativity shows the limits of motion and spacetime under extreme conditions, another branch of physics is investigating whether time as we know it is truly fundamental at all. Quantum connections to time. Quantum research adds yet another dimension to the mystery of time. While relativity explains how time changes with motion and gravity, quantum mechanics presents effects that seem to operate outside those same limits. One of the most striking examples is quantum entanglement, where two particles can remain interconnected no matter how far apart they are. When one is measured, the other shows a correlated outcome instantly, even across kilometers of separation. Experiments confirm this behavior with remarkable precision. At first glance, it seems to ignore the speed of light as an upper bound, raising profound questions about whether time operates in the same way on quantum scales. A landmark moment came in 2022, when the Nobel Prize in Physics was awarded to Elaine Aspect, John Clauser, and Anton Zeilinger for their experiments on entanglement. Their work ruled out explanations based on hidden variables, showing that entangled particles do not carry preset instructions determining their properties. Instead, the correlations appear at the instant of measurement itself. This means the definition of an entangled system is not split between two objects but formed as one whole, even when separated by vast distances. For decades, physicists wondered whether hidden connections could explain these correlations, but the Nobel-winning results confirmed that quantum mechanics resists such classical interpretations. Yet entanglement, despite its extraordinary behavior, cannot transmit usable information faster than light. This is a critical distinction supported by the so-called no-signaling theorem, which ensures that instantaneous-looking correlations cannot be turned into signals or messages. When one particle is measured, the result is random. Only after comparing it with its partner do the correlations become evident. Relativity therefore remains intact. No cause and effect chain can be disrupted, and no observer can exploit entanglement to send communication faster than photons can travel. What makes entanglement striking is not its ability to violate relativity, but the way it reveals a form of linkage that seems to occur without reference to time or distance. This sharpens the puzzle. If the correlations exist without delay, how should they fit into our picture of physical reality? Some theoretical models propose that time itself may not be fundamental, but instead something that emerges from deeper patterns, such as networks of entanglement or arrangements of quantum information. In this view, time could play the same role temperature does in thermodynamics, not a property of any single particle, but a statistical outcome of countless quantum processes interacting. Importantly, this remains an active area of research rather than a settled fact. Physicists debate whether these models can be reconciled with relativity and whether they can generate testable predictions about the role of time at the most basic level. Connecting this perspective to light speed adds weight to the discussion. For photons, relativity assigns zero proper time along their paths, meaning that from a mathematical standpoint, a photon is not associated with any ticking of an internal clock. Similarly, entangled particles show correlations that are not delayed by distance or time. Both cases appear to sidestep the kind of gradual progression we associate with seconds and minutes, suggesting that what we experience as the steady flow of time may apply only to massive systems like us. If information in entangled states and particles at light speed both act outside ordinary time, then our notion of temporal order may belong more to macroscopic observers than to the deepest layers of physics. This possibility pushes research beyond metaphors. In laboratories, physicists test entanglement across ever larger scales. Fiber optic cables span city networks, distributing entangled photons across tens of kilometers. Satellites transmit entangled pairs between continents, proving the effect holds up even under orbital conditions. These experiments consistently show no measurable delay and no weakening of correlations with distance. Precise atomic clocks on each end confirm that synchronization does not depend on standard timekeeping. The link is intrinsic to the entangled system. At every test, entanglement appears untouched by temporal limits. The implication is that quantum relationships can coordinate without relying on time as an intermediary. This does not mean time has no role in physics. It clearly governs the unfolding of events we observe. But it may mean that on a deeper level, time emerges only once systems reach complexity and scale. At the limit of entanglement, correlations lock instantly, no matter the physical gap. At the limit of light speed, proper time compresses to zero. Together, these hints suggest that time may not be uniform across nature's layers, but instead contextual, indispensable for massive observers, dispensable for photons and entangled states. Physicists have proposed multiple frameworks to capture this. Some link time to entropy, arguing that what we call the arrow of time is tied to the growth of disorder in large systems. In this conception, measurement introduces entropy, while entanglement itself remains pristine until an environment interacts with it. Others borrow the holographic principle, proposing that time could derive from information encoded in deeper structures of reality, surfacing only when we analyze it at larger scales. These approaches remain speculative, but are gaining attention precisely because experiments on entanglement continue to support the idea that correlations arise without dependence on ordinary time intervals. Quantum entanglement also undermines classical locality, the rule that an object here cannot affect something there without a process bridging the distance. No classical concept accounts for how entangled partners appear connected across space without communication. If locality is not absolute, then our descriptions of space and time may be effective tools rather than fundamental features. On macroscopic scales, locality and time hold firmly, shaping orbits, clocks, and navigation systems. But beneath that layer, they may not be built into reality at all. Entanglement shows that at the quantum level, the universe can display a different order, one where the distance between events and the intervals separating them do not dictate outcomes. For understanding light speed, this has profound consequences. Relativity tells us the speed of light sets a ceiling for information transfer through space. Quantum mechanics shows correlations that need no transfer mechanism. Both perspectives could be describing different sides of the same coin. Relativity works where time and causality structure events, while quantum theory hints at a deeper level where neither is fundamental. In this picture, the photon's zero proper time and entanglement's apparent timelessness are examples of how differently the universe behaves once you step outside the macroscopic frame that defines human experience. New experiments continue to sharpen this picture. Around the world, physicists are entangling photons over continental distances and verifying correlations with picosecond precision. Despite ever finer tests, no sign of time delay has emerged. The results suggest that whatever mechanism underlies entanglement does not rely on ordinary temporal flow. Instead, it reveals connections that seem permanent, universal, and in no way constrained by the ticking of clocks. All of this places time in a new light. Relativity demonstrates how time slows as velocity increases, approaching but never reaching a halt. Quantum mechanics shows situations where correlations appear without any reference to time. Between them, researchers face one of the most profound challenges in physics, deciding whether time is an element of the universe or the result of deeper quantum structures. The debate is ongoing, with each new experiment probing how robust our assumptions truly are. And while these questions continue to expand the scope of what time might be, one constant remains central to all of physics: the role of light itself. Relativity makes it the limit for motion. Quantum theory makes it part of the puzzle of timelessness, and experiments in 2025 are testing its behavior with more precision than ever before. Whether light speed is fixed everywhere under all conditions remains one of the most significant tests still unfolding. New 2025, precision in the speed of light. In 2025, one of the most active frontiers in physics concerns how precisely we can test the stability of light speed. For more than a century, the assumption has been that this velocity is a universal constant. It shapes relativity, underpins measurements of distance, and appears in every formulation about how the universe expands. Yet the push for ever sharper precision continues, both in laboratories on Earth and through observatories looking back to the earliest cosmic eras. What has changed is the balance between two types of testing: extremely controlled experiments that refine confidence in light's constancy close to home, and telescope observations that expose potential anomalies across immense distances. The tension between these results is what makes 2025 such a pivotal moment for understanding this constant. On the laboratory side, technology has reached astonishing levels of accuracy. Optical lattice clocks operating with ultra-cold strontium atoms now measure time with stability fine enough to detect relativistic effects over vertical distances of just a few millimeters. JILA's 2022 demonstration of gravitational redshift across that tiny scale stands as one of the clearest examples. Two clocks separated by the thickness of a grain of rice tick at slightly different rates, just as Einstein predicted. The advance shows not only how extraordinary atomic clock precision has become, but how directly tied these instruments are to confirming the reliability of light's speed as it appears in Maxwell's equations and relativity. Each refinement cuts into the uncertainty margins, and every local test reconfirms that within Earth's influence, photons behave with remarkable uniformity. At the same time, cosmological observations continue to generate puzzles. Data from the James Webb Space Telescope have intensified long-standing tensions about distance and expansion. Its images of early galaxies, some forming surprisingly soon after the Big Bang, look inconsistent with expectations derived from decades of redshift measurements. Standard cosmology depends on extrapolating how much the wavelengths of light stretch as space itself expands. Yet when Webb reports galaxies that appear too developed for their measured redshifts, scientists are forced to confront two possibilities. Perhaps galaxy formation occurred sooner and more rapidly than models allow, or perhaps our assumptions about light's constancy across billions of years need re-examination. This debate echoes the earlier Hubble tension, where independent measures of the universe's expansion rate disagreed by margins too large to dismiss as error. The important point is not that light speed has suddenly changed, but that the models based on its constancy are being stressed by new evidence. Researchers remind us that in the International System of Units, the speed of light has been defined exactly since 1983 at 299,792,458 meters per second. In practice, this means the meter is calibrated to that fixed quantity. When physicists speak of testing C, they are not hoping to adjust the SI number itself, but checking whether photons behave precisely as expected under extreme circumstances. The difference is subtle but critical. Laboratory work verifies the constant within controlled conditions, while astrophysical signals probe whether unknown effects might alter the way light preserves its properties on scales unimaginably large. Locally, experiments continue to reinforce confidence. Cavity resonators, interferometers, and quantum optical standards locked to atomic clocks achieve agreement to ever finer digits. Ultra-stable lasers keep frequency drift so low that even seismic waves and thermal fluctuations are measurable sources of noise. Within these purified vacuums and chambers, every photon tested conforms exactly as relativity predicts. No difference emerges that would challenge the idea that C is inviolable for all practical use. This underlies technologies like GPS, which only work because engineers can count on uniform light speed when converting satellite signals into distances measured on the ground. For networks, navigation, and communication, the data confirm stability day after day. Cosmology, however, operates at scales where no laboratory can mimic the conditions. Light reaching us from galaxies billions of light years away has crossed regions of intense density, evolving structure, dark matter, and dark energy. Any deviation observed in those signals may point not to light itself changing, but to overlooked mechanisms shaping how it travels. Suggestions include complex distributions of cosmic dust, gravitational lensing by massive structures, or inaccuracies in assumptions about the timeline of star formation. Advocates of strict constancy emphasize that extraordinary claims demand extraordinary evidence, and the anomalies may eventually be absorbed through refinements of astrophysical models rather than revisions of physical constants. And yet the anomalies persist. The numbers recorded by Webb do not align neatly with what models predict. Certain galaxies appear older, more massive, or more chemically enriched than expected at their redshift values. Some researchers argue that if photons did behave differently in the early universe, even by the smallest margin, it could ripple through the entire structure of cosmology. Expansion rates, dark energy models, and the chronology of structure formation would all require recalibration. The possibility remains speculative, but it keeps the debate alive by forcing attention to where our current frameworks struggle. This split between local precision and cosmic puzzles shapes the ongoing research landscape. If light speed is confirmed absolutely unchanged, then any misalignment of galaxy ages or distances signals the need for other corrections, perhaps involving dark matter clustering or new physics behind cosmic inflation. If evidence someday suggests that light behaves differently under extreme conditions, it would mark one of the most profound shifts in modern science. Either result sharpens clarity. Constants remain constant until experiments prove otherwise, and new environments test those claims. The effort itself shows why physics never accepts values as permanent without continued challenge. For now, the evidence remains weighted toward stability. Every controlled terrestrial test reaffirms uniform results, even at interplanetary distances where signals bounce between spacecraft and Earth. Timing agrees with the constant defined in SI units. Only at cosmological ranges do cracks appear in the seamless picture, and even there, the consensus holds that better understanding of astrophysics may explain them. But questions about absolute constancy sharpen scientific focus and encourage the refinement of both instruments and models. The wider significance lies in how constants function in scientific practice. By definition, they establish frameworks that allow predictions, navigation, and engineering to work consistently. Questioning them does not diminish their importance. It strengthens the durability of the foundation. Light speed, gravitational constants, and other fixed figures endure because tests keep verifying them under harsher and more diverse conditions. When anomalies challenge them, the result can either be reinforcement through deeper confidence or correction through a new standard. Both outcomes advance scientific knowledge. What emerges in 2025 is neither sensational collapse nor final closure but a clearer contrast. On one side, ultra-precise clocks and laboratory tests confirm unchanging photon behavior under ordinary and slightly extreme terrestrial conditions. On the other, Webb's celestial observations raise questions about how accurately we are reading the early universe and whether hidden influences distort our interpretation of ancient light. Instead of claiming that C has varied everywhere, the responsible framing is that astrophysical anomalies prompt new reasons to retest assumptions at the largest scales available. In this balance lies progress, reaffirming what holds locally while pressing on the areas where confidence is less established. This pursuit also frames how we think about time itself. Constancy at familiar scales supports the technology society depends on daily. Anomalies in distant light remind us that the universe may hold environments so foreign that even its deepest principles deserve checking. The process keeps physics alert to overlooked influences and safeguards against treating constants as unquestionable truths. As these questions remain under investigation, the focus of research also touches on how humans interact personally with the effects of relativity. For scientists, measuring C defines the structure of the cosmos. For astronauts, differences in timekeeping are not abstract but physical experiences shaped by their velocity and position. That everyday dilation of time, long confirmed by experiments, becomes visible on every orbit above Earth's surface. Reality bending in practical space travel. When considering how relativity shapes daily life in orbit, the subject becomes more than abstract physics. It becomes a practical matter for space agencies and astronauts. Reality bending in practical space travel emerges whenever humans leave the ground, because even at modest orbital velocities, the flow of time is no longer identical for everyone. What happens in Earth's laboratories, or with GPS satellites, extends directly to astronauts circling the planet, and, increasingly, to those preparing for long interplanetary journeys. On the International Space Station, astronauts move at nearly 28,000 kilometers per hour as they circle Earth every 90 minutes. At that speed, combined with their position in a slightly weaker gravitational field than those on the surface experience, the crew's clocks run differently than ours. The difference is extremely small, but it is measurable. Over weeks and months, the discrepancy grows into fractions of a second. This means an astronaut returning from orbit has aged imperceptibly less than someone witnessing the same span of days on Earth. Though the effect cannot be sensed personally, it is encoded in the physical structure of their bodies and in every clock they carry. One of the clearest recent demonstrations of this involved astronaut Scott Kelly. In 2015 and 2016, he spent nearly a year aboard the ISS, while his identical twin, Mark Kelly, remained on Earth. This created an opportunity to compare two biologically matched individuals with differing experiences of time. Scott's high orbital speed and weaker gravitational field meant that time passed just slightly slower for him than it did for his brother. The difference was tiny, on the order of milliseconds, but conclusive. When they reunited, Scott had aged very slightly less than Mark, providing a human-scale confirmation of Einstein's predictions. The so-called twin experiment reinforced what equations had already established and made time dilation a lived, measurable reality for a human being. For space programs, this is not a scientific footnote but an operational necessity. Just as GPS satellites must correct their internal timing to remain functional, spacecraft systems demand the same precision. Navigation requires clocks that sync between Earth and the crew. Communications depend on tightly aligned timing to transmit and receive signals, and life support systems use sensor networks calibrated against reliable standards. Even millisecond differences accumulate into hazards when missions stretch for months or years. Relativistic adjustments are therefore programmed directly into mission planning, ensuring every system stays coherent as spacecraft traverse millions of kilometers. No agency can overlook these corrections. When ground control sends a signal to a spacecraft, it must anticipate the time offset arising from both distance and relativity. Commands, telemetry, and coordination between onboard computers and Earth must account for the fact that the ship is moving through a different temporal frame. Each step requires active assimilation of the laws Einstein described more than a century ago, transforming what was once a theoretical prediction into a mandatory engineering tool. The International Space Station, though crucial for testing these ideas, represents only the beginning of the challenge. Missions under design in 2025 extend the problem into new territory. NASA and the European Space Agency are preparing for extended journeys to Mars, where astronauts may spend 2 to 3 years away from Earth. Over such durations, relativistic effects, still minuscule compared to light-speed travel, continue to build. Astronauts will return with subtle but measurable differences in elapsed time compared to those who remain behind. These offsets are not just curiosities. They must be anticipated to maintain precise navigation, docking, and landing sequences on missions measured in hundreds of millions of kilometers. The numbers help illustrate the stakes. The Mars-Earth distance can vary from about 55 million to over 400 million kilometers depending on orbital alignments. A microsecond error in timing translates into hundreds of meters, discrepancy in arrival coordinates. For a landing sequence, this margin could spell the difference between descending securely onto a pre-chosen site and touching down kilometers away from safety. The onboard slowing of clocks, small though it seems, becomes multiplied into real positional risks. By routinely integrating relativity corrections, agencies reduce these risks and ensure that astronauts can arrive and return reliably. The role of upcoming technology highlights this priority further. In 2025, the European Space Agency will launch the Atomic Clock Ensemble in Space, ACES, aboard the ISS. ACES is designed to operate as the most precise orbital clock network yet, comparing ultra-stable space-based atomic clocks directly with clocks on Earth. This experiment will test relativity's predictions in practice, while also demonstrating how future missions might maintain synchronization across the solar system. The project brings clock precision into orbit as both a physics experiment and a precursor to interplanetary navigation, closing the loop between theory, engineering, and operational reality. Looking further ahead, mission concepts involving nuclear thermal or nuclear electric propulsion would drive spacecraft to higher velocities than chemical rockets can achieve. These designs promise shorter transit times, but they also intensify relativistic effects. The time offsets become somewhat larger from the perspective of Earth observers, and more pronounced corrections are required for mission planning. At human timescales, astronauts would still only age slightly less than people on Earth, but for the systems that stabilize and guide their journeys, every narrowing margin adds significance. Each technological step forward amplifies the impact of relativity, embedding it ever more deeply into exploration. Beyond engineering, such differences raise questions about how societies might interpret human time in space. If crews traveling to outer planets age fractionally less, or if future faster transports heighten the discrepancy, planning will need to address not just technical but human consequences. Colonists leaving Earth may remain biologically younger by small margins than peers they left behind, a fact that complicates communication schedules, mission documentation, and even cultural perspective. While differences of milliseconds today are trivial, they preview more dramatic contrasts if humanity pursues trajectories closer to relativistic speeds. It is important to note that none of these outcomes signal an error in machinery or cognition. They are not problems to be fixed, but features of how spacetime operates. One clock on Earth and one in orbit are both right, according to the reference frames they occupy. The difference is physical law unfolding in practice. Recognizing this removes ambiguity for engineers and astronauts. The task is not to reconcile clocks to a single universal rate, but to embrace relativity as a condition of travel, integrating it into every system that depends on precision. By 2025, the influence of relativity is unmistakably visible in human exploration. Instruments like ACES anchor the corrections needed for upcoming missions, while the Scott Kelly experiment remains a reminder that differences in time are lived experiences, however slight. For mission planners, equations that once appeared alongside thought experiments now appear as mandatory algorithms in computer models. The same physics that bends light and guides satellites today is written into the blueprints for journeys beyond Earth orbit. As ambitions stretch outward, relativity becomes the fabric through which every milestone is achieved. It is carried in the microseconds separating twin brothers' biological ages, in the nanosecond precision of atomic clocks on the ISS, and in navigation software preparing crewed paths to Mars. Practical space travel has become a theater where reality bends in ways ordinary life on the surface never requires us to notice. The spacefaring future will depend on continuing to respect those distortions, integrating them as fundamental truths of operation. The natural next question follows from this. If time changes for astronauts and spacecraft as relativity dictates, what does that imply about the nature of time itself? Beyond operational corrections and mission planning, scientists are asking whether time exists as a fundamental property at all, or whether, as new theories suggest, it may be something that emerges from deeper structures in physics. Theoretical breakthroughs from 2025. In 2025, several new theoretical breakthroughs have drawn attention to ideas that could reshape how physicists think about time. Rather than assuming time is one of the universe's most basic ingredients, some researchers have shifted toward treating it as a consequence of deeper structures. In this approach, time would not exist on its own, but would instead arise from correlations within physical systems. The goal of these models is to create a possible bridge between general relativity and quantum mechanics, two frameworks that remain difficult to reconcile. These ideas remain explorations rather than established facts, but they highlight how active the search has become for a more unified picture of the universe. A significant part of this exploration is tied to quantum entanglement. When two particles are entangled, their properties remain connected no matter the distance separating them. Measurements of one align with the state of the other, even when they are kilometers apart. In 2025, theorists have drawn on this behavior to suggest that what we call time could itself be a large-scale consequence of such correlations. Instead of an independent flow, the sequence of past, present, and future would emerge, because entangled systems create consistent patterns of cause and effect. If this interpretation is correct, then time does not stand apart as a universal backdrop, but develops from how particles interact with each other. Another powerful framework comes from the holographic principle, which arose in studies of black hole thermodynamics and later expanded through string theory. It proposes that all the information in a three-dimensional region of space can be stored on a two-dimensional boundary. In some models, this projection includes both space and time, pointing to the possibility that our three-dimensional experience of time is not fundamental, but an emergent surface description of a deeper reality. It provides a vivid metaphor. Just as a hologram encodes a three-dimensional image on a two-dimensional plate, the flow of time we experience may be encoded on a boundary, not part of the deepest layer of physics. For scientists exploring emergent time, this principle strengthens the case that both space and time might be byproducts of more elementary structures. This line of thinking appeals to researchers trying to resolve the long-standing mismatch between relativity and quantum theory. General relativity describes the curvature of spacetime and the role of gravity across large scales, while quantum mechanics describes probabilities and correlations at very small ones. Each theory succeeds in its own domain, yet attempts to apply both simultaneously. For example, at black hole singularities or in the first moments of the universe, expose contradictions. If time itself is emergent, relativity's description of time could be interpreted as a higher-level outcome, while the quantum layer would provide the rules from which that outcome arises. This does not make relativity incorrect. Instead, it frames relativity as an excellent emergent theory for macroscopic clocks and massive bodies, while more fundamental processes govern behavior at the smallest scale. The challenge is that this perspective requires rethinking familiar assumptions. Physicists may be describing only part of reality when they speak of time slowing at high velocity or halting for photons. In emergent interpretations, those effects describe surface behavior, comparable to the way waves appear on top of an ocean. The waves are real in the sense that they can be measured and studied, but they depend on deeper water beneath them. Similarly, time could be real for observers like us without being fundamental. At its base, the universe might contain only correlations and quantum states, from which the appearance of flowing time gradually emerges once complexity reaches certain levels. This proposal also affects how scientists think about constants such as the speed of light. In relativity, photons are assigned zero proper time. They travel along null paths where the familiar flow does not apply. If time is emergent, then this feature is not an anomaly but an indication. Photons would not experience time, not because they are exempt from a universal rule, but because they are too simple for emergent time to appear within them. Only complex systems generate the conditions necessary for time to exist as we perceive it. This conditional phrasing is crucial. These proposals have not been experimentally verified. They remain theoretical instruments for probing how the universe might be constructed at its most basic level. Some models in 2025 go further by tying emergent time to entropy. Entropy is already understood as the measure of disorder or complexity in a system, and it underlies the so-called arrow of time. In emergent time approaches, entropy growth is not just an arrow, but the very structure from which time is built. Correlations between quantum states produce patterns that increase in disorder, and our experience of time flowing forward is the macroscopic recognition of this trend. If the system's complexity did not increase, there would be no clear temporal direction. Time in this view would be the record left behind by rising entropy, not a pre-existing dimension. Critics emphasize that such ideas face major obstacles. It is one thing to describe time as a statistical outcome of entropy or entanglement, but another to explain why time appears continuous and reliable in the macroscopic world. Any valid model must reproduce the causality we observe in daily life. Causes consistently precede effects, and physical laws unfold predictably. Without this, emergent frameworks cannot serve as replacements even at a conceptual level. Supporters note that relativity, too, began as a radical departure and required decades of scrutiny before widespread acceptance. They argue that emergent time models deserve exploration, not because they are proven, but because they might address puzzles relativity alone cannot solve. One important clarification is that relativity remains indispensable for describing how clocks and bodies behave at every accessible scale. Experiments on satellites, accelerators, and spacecraft continue to confirm its predictions without exception. Emergent time theories do not aim to discard relativity. Instead, they attempt to provide a deeper explanation of why relativity works so consistently. Just as temperature emerges from countless microscopic particles while still behaving reliably as a thermodynamic quantity, time could emerge from quantum correlations while still behaving as relativity describes for planets, clocks, and human travel. In this sense, relativity would not be invalidated, but placed as the high-level, effective theory for macroscopic timekeeping. These tentative models invite physicists to reconsider familiar questions in new terms. Why does time appear to slow asymptotically as speeds approach the speed of light? Why do photons follow paths with zero proper time? Why are entangled states linked in ways that seem independent of ordinary temporal order? Instead of treating these as disconnected anomalies, emergent time perspectives suggest they may all be aspects of the same underlying structure. If time only exists where systems build it through complexity and entropy, then relativity's predictions and quantum mechanics, correlations could be unified under the same principle. The work remains purely theoretical, with no experimental proof yet available, but the interest it has drawn in 2025 reflects a growing recognition that progress on the deepest problems of physics may require revisiting what has long been seen as basic. If future research succeeds, it could clarify conditions at black hole horizons, or in the earliest instance after the Big Bang, two contexts where our current understanding breaks down. If it fails, it may still sharpen the questions and guide scientists toward more consistent frameworks. Either way, the investigation is forcing a closer look at the foundations of reality. Reconsidering time at this level has implications that stretch beyond theory. If time turns out to be an emergent outcome of quantum correlations and entropy, then it means the flow we perceive is both real and conditional. Real because it binds our world together, but conditional because it may not appear universally at every scale. That insight could one day guide how we think about travel, communication, and causality on cosmic distances. Even though these models remain untested, They highlight new ways scientists might approach limits such as the speed of light, not by trying to break them, but by questioning what the boundaries themselves truly mean. In that sense, the breakthroughs of 2025 draw research closer to practical questions that have long fascinated humanity. If time can stretch, link, or emerge from deeper processes, then the rules we observe in relativity may provide paths for imagining possibilities in exploration. From here, the puzzle moves naturally toward a wider perspective. What such insights could imply not only for physics, but also for how humans might approach the challenge of traveling to the stars. What this means for humanity's future. Humanity's long-term future depends on how we respond to the boundaries that physics defines. When considering interstellar travel, it is clear that the speed of light will not be crossed by ships or cargo, yet the search for possible routes forward continues. What does this mean for us as a species? The answers lie not only in visionary theories, but in the near-term realities of propulsion, the refining of speculative physics, and the role of public imagination. Understanding what we can achieve now, what remains under study, and what will almost certainly remain unattainable with today's technology gives the clearest picture of our future in space. At the scale of practical engineering, the near-term ambitions focus less on exotic scenarios and more on propulsion methods we can reasonably build and test. Advanced chemical rockets still power all crewed launches and remain central for lifting heavy payloads from Earth. But for deep space, nuclear thermal and nuclear electric propulsion stand out as the most plausible steps forward. Nuclear thermal engines, which heat propellants directly in a reactor, can deliver far greater efficiency than current chemical systems, reducing the time it would take to reach Mars or the outer planets. Nuclear electric concepts, which convert nuclear energy into electricity to drive efficient ion or Hall thrusters, offer even higher performance for carrying heavy payloads slowly but steadily across vast distances. These technologies do not approach relativistic speeds, but they could shorten interplanetary missions, transforming Mars journeys from multi-year odysseys into expeditions spanning months. This incremental progress marks the path toward realistic expansion into the solar system. Seen in this context, the emphasis on nuclear systems is not a retreat from ambition, but the beginning of scaling up beyond conventional rockets. The distances alone demand it. Voyager 1 and Voyager 2, launched with the best chemical boosters of their day, have crossed into interstellar space, yet their centuries-long transits to nearby stars make clear how ineffective such propulsion is for human purposes. Reaching even the closest stellar neighbors would still take tens of thousands of years using such methods. As impressive as their achievement is, it underlines how limited current propulsion remains, and why agencies look urgently toward advanced nuclear or hybrid options as the ground floor of realistic exploration. Warp drives and other space-time engineering concepts capture imagination, but belong to a different category. Speculative frameworks where the mathematics may appear consistent, yet experimental evidence and engineering approaches are absent. Miguel Alcubierre's original metric required negative energy densities, an ingredient not available in nature except in minuscule laboratory effects like the Casimir vacuum, which are far too small for practical application. Subsequent refinements published through the 2000s and 2010s have chipped away at the energy tallies, suggesting that warp geometries with ring-shaped configurations or layered bubbles could reduce demands by colossal orders of magnitude. More recently, in the 2020s, theorists have proposed models that in principle might work with positive energy densities, hinting that the gap may not be as absolute as once thought. Yet none of these metrics is anything close to experimental physics. As of 2025, not a single laboratory has created or even observed a warp bubble of measurable magnitude. On paper, energy requirements can be lowered, rebalanced, and restructured, but this remains a computational exercise. Supercomputers and AI algorithms contribute by scanning enormous parameter spaces, mapping possibilities for bubble geometries that distribute stresses more evenly or demand less exotic input. These refinements are valuable for theoretical clarity, but they do not constitute proof of feasibility. The divide between what would be needed to produce a bubble and what is currently achievable is vast. Clarifying that distinction is vital. Theoretical research can redefine limits, but no experimental demonstration yet points toward a path for constructing warp technology. Even if future breakthroughs one day validate some form of spacetime engineering, the cultural framing will matter as much as the mathematics. Communication plays a central role in how propulsion research is understood. Warp drive studies often veer between exaggerated media claims and overly skeptical dismissal as pure fiction. For research to remain alive, scientists must present results to the public in accessible terms, neither promising imminent starships nor rejecting their relevance outright. Public support influences funding, and international cooperation will be needed for any major development. Clear communication ensures that warp research is perceived as exploration of physical law, not proof of unreachable fantasy. Along this path, subluminal warp configurations could eventually serve as intermediate steps. These designs, traveling below the speed of light, do not face the same causality concerns that plague faster-than-light models. While they would not enable instant interstellar travel, they could reduce the duration of trips inside the solar system. A properly engineered subluminal drive shortening Earth, Mars journeys, or enabling rapid access to the outer planets would already represent a transformative development. Such progress could lay groundwork for further refinements. But again, as of today, there is no experimental prototype, only numerical simulations and theoretical possibilities. Another factor shaping humanity's future in space is computing power. Modeling warp spacetime structures already pushes the boundaries of what supercomputers can handle. Each configuration requires detailed evaluation of energy flows, boundary conditions, and stability measures. Artificial intelligence supports this process by optimizing parameters and flagging metrics that could be numerically viable. If spacecraft were ever to carry such systems on board, real-time adaptive computing would be essential. Automated control would handle bubble stability, trajectory corrections, and responses to unexpected conditions far more capably than manual piloting. For the foreseeable future, however, the role of computing and AI is to accelerate research at the simulation stage, where refinements remain strictly theoretical. The human implications of relativistic travel, even in principle, remain profound. If astronauts on near-light-speed journeys could experience years while centuries pass outside, societies on Earth would change in ways the travelers themselves could not share. Colonies founded under such time differences would quickly diverge in culture and identity, bound to Earth only by signals delayed across decades or centuries. Communication would break down not for technical reasons, but for temporal ones, with exchanges slowed to the pace of interstellar distances. This cultural dimension reinforces the magnitude of the challenge. Interstellar travel would demand reinvention not just of propulsion, but of social expectations. Closer to home, relativity still offers conceptual benefits even for missions far short of light speed. Crews on faster nuclear or hybrid-driven vessels would experience slight time dilation, aging imperceptibly less than contemporaries on Earth. For missions within the solar system, such differences are measured in milliseconds or seconds, not years, but they show relativity operating even in environments we may soon inhabit. The effect is real, but the challenge is scaling it up into forms that matter for journeys across stars. Looking at all these strands, nuclear propulsion, warp metrics, AI support, cultural adaptation, the payoff is not a definitive path to the stars tomorrow, but incremental steps forward. Relativistic effects provide conceptual advantages, such as time dilation, but the engineering and energy hurdles leave human missions to other star systems far beyond present technology. What humanity can achieve in the near future is continued expansion into the solar system with realistic propulsion advances, deeper theoretical work into spacetime models, and broader technological growth driven by computing and collaborative science. Each breakthrough, whether or not it leads directly to interstellar travel, expands the range of possibility for future generations. The meaning of this for humanity's future is both sobering and inspiring. Sobering in that the dream of starflight will not be realized with the tools currently available. Inspiring because each step of research strengthens our grasp of the universe's rules and generates technologies with uses far beyond the original vision. Exploring warp models may sharpen cosmology. Pursuing nuclear thermal engines will make Mars expeditions more practical. Enhancing AI and computing resources propels innovation across all domains of science. All of these strands matter, regardless of whether warp drives ever leave the whiteboard. The outline that emerges in 2025 is therefore one of layered ambition. Short-term, nuclear-based propulsion and improved rockets guarantee progress within our solar system. Medium-term, refined theories clarify what spacetime might permit in principle. Long-term, no promise is certain, but the commitment to test, model, and question could one day produce options we cannot yet picture. Humanity's future remains chained to physics, but unbounded in imagination. The payoff is steady motion outward, step by step, through technologies that test our ingenuity against nature's limits. To grasp the implications sharply, it is enough to say this: relativity opens conceptual doors, quantum theory hints at deeper structures, and both together inspire us to test what seems impossible. What remains clear is that the universe enforces boundaries that no amount of ambition can casually erase. Our next advances will not erase those boundaries, but will make them more visible, usable, and precise. And in our own time, even before talk of warp drives or interstellar colonies, the evidence for relativity and its impact on humanity's future can already be measured in the systems we build and the technologies we rely on. This recognition carries a forward-looking consequence. The physics that may one day frame ambitious exploration is also at work around us now, shaping the tools and instruments on which our societies depend. Time dilation remains more than theory. It is proven in practice. GPS satellites, for instance, would drift by about 38 microseconds per day without relativistic corrections, leading to navigation errors of kilometers. Such corrections prove Einstein's predictions every time you check a map. At the same time, precision experiments keep pushing limits. JILA's atomic clocks can detect gravitational redshift across a millimeter, and the Large Hadron Collider accelerates particles to 99.999999% of light speed, stretching lifetimes exactly as relativity demands. Beyond this, speculative ideas like warp drives or emergent time theories remain active research topics, fascinating but unproven. In the comments, tell us which you find most convincing: tested systems like GPS and atomic clocks, accelerator experiments, or speculative theories about emergent time, and why.